let's go a little bit more deeper on the materials of carbon fuel cells, multi-carbonate fuel cells. So basically, usually we have at the anode an anode catalyst that is nickel based and is usually an alloy of nickel with chromium or nickel with aluminium. Then what is the peculiarity of this technology is that the electrolyte is molten. That means that we will have a molten phase that is usually made by molten salts that are lithium carbonates or potassium carbonates. That usually, as a technology, require to be, of course, good conductor of carbon ions that needs to migrate from cathode to the anode, and at the same time, good isolator to avoid a mixture between reactants, so to make a barrier to avoid oxygen and hydrogen to get in contact and react chemically. And we have to, at the same time, to avoid the electrolyte consumption because reaction corrosion or can reduce the concentration of these molten salts in the electrolyte, or we may have potential driven migration that accumulate the molten salts in one side of the cell, reducing the concentration and the distribution, a uniform distribution along the electrolyte, and also to avoid salt vaporization. These are issues mainly related to the electrolyte. But what is peculiar of this technology is that the electrolyte, as fluid, needs to be kept physically in a sort of sponge that is the matrix, that is usually made of lithium aluminates, and usually it becomes, of course, the thickness of the electrolyte itself because it's the solid phase, and so the thickness has an effect on the durability of the cell and also on the several thermal equilibrium, such like thermal cycling, that may have an issue on that. But what also is important is that compared to other cells, the matrix itself is also the sealing, so we don't need to use additional sealing, but the matrix becomes also the sealing of the technology. If we look to the cathode side, usually we use nickel oxide lithiates as material, but the issue, of course, of the cathode is in the barrier between the cathode and the electrolyte. So it's important to establish a stable electrolyte gas interface with a porous electrode. And what is important is to design the electrode to correctly balance the pressures of reactants, in this case oxygen and carbon dioxide. We need to also prevent the cathode dissolution in the electrolyte because what can happen is that the nickel oxide can react directly with carbon dioxide with a big issue for this technology, that is the production of ions, nickel ions, not only carbonates, and the risk is that nickel ions can migrate through the electrolyte, reaching the anode, in which they react with hydrogen and carbonates to produce nickel. So we have a sort of migration of nickel from as a catalyst from the cathode to the anode. And especially what is a big problem is that we may have a precipitation of nickel in the matrix, and especially it becomes a conducing, so we have a short circuiting across the matrix, so we risk to close in an inappropriate way the circuit inside the fuel cell. So how to avoid this process? Of course, we have a control in the cathodic gas composition to maintain low carbon dioxide partial pressure. Or what's more, we usually can modify the material of the cathode. So we can use nickel-free cathodic catalyst like lithium ferrate, manganate, or cobaltum-based oxides. Or at the same time, we can operate in the molten salts, so in the electrolyte, to reduce the risk of acidity using additives like carbonates based on calcium, strontium, or barium. Or we can substitute the molten salts with lithium potassium or lithium sodium in the electrolyte that will reduce the nickel oxide solubility and keeping a good ionic conductivity and low chemical aggressive behavior.